Let's take a look at Newton's famous second law of motion. And to help us, we're going to be using the PHET Physics website, which has got lots of simulation to help you understand physics. A wonderful site, and there'll be a link on the website. So here's the investigation we're going to be looking at. We're going to be looking at this wooden crate, which has got a mass of 50 kilograms. It's going to be sitting on a skateboard, and there's going to be no friction between the wheels and the bearings of the wheels, so we don't need to worry about friction at all, not even friction with the crate and the air. The man is going to be providing the force by pushing the wooden crate, and above the man's head is going to be a speedometer, which will help us see how the speed is changing when the force is applied. So let's go ahead and apply a force to the crate, and the first force we'll apply is the following. It's going to be a 50 Newton force. And you can see what's happening. The speed is beginning to increase. And a rough calculation tells us the speed is increasing about roughly 1 meters per second every second. So that is the crate accelerating. So when we apply that 50 newtons force, it's going to be accelerating. If we take the man away from the push, we can see that the speed will remain constant after that. And that's a very important thing to understand. You don't need a force or an unbalanced force to keep something moving. Once something is moving, that is, once it's on its way, according to Newton's first law, it will continue in that state of motion until another unbalanced force acts upon it. Now the next thing we're going to do is reset things and actually use a bigger force to see what happens to the acceleration. So we'll bring the little wooden model back. We'll show the values, the mass and the speed, and this time we will increase the force applied to the wooden crate and observe what happens to the speed. So this time we're going to apply a 100 Newton force. That's double the force. And you can see the speed is increasing a lot more. So what we've learned from here is that the speed is actually increasing a lot more from that double force. Once the man stops pushing, you can see the speed remains constant. So once again we get from that, you don't need an unbalanced force to keep something moving. But what we have noticed there is that if we increase the force applied to the object, the wooden crate here, keeping the mass the same, we see that the increasing speed gets bigger. In other words, increasing the force applied to the wooden crate will result in an increase in that wooden crate's acceleration. The bigger the force applied, the bigger the acceleration. Now let's explore what happens if we apply a force to the wooden crate but then change the mass of the crate. Now to do that, we'll change the object from, say, the 50 kilogram crate to a 200 kilogram fridge. So by changing the mass and keeping the force the same, we'll investigate what happens to the acceleration or the increasing speed that occurs. So let's go for this one then. We start off with the 50 kilogram crate. I'm going to stick with the same force. We're going to stick with 50 newtons, and as we saw before, you can see the unbalanced force is causing an acceleration of the crate, and the acceleration is roughly about 1 meters per second every second. If we stop pushing, the man will move away, the trolley will keep moving away from him, but it will move away with the same speed. Remember, we're not dealing with friction here, there's no friction involved. So let's bring everything back to again, and this time rather than the wooden crates, we shall get rid of the wooden crate, we're going to be using maybe double the wooden crate this time. So put one crate there and a crate on top like that. So we've doubled the mass of the object which the man is going to be pushing. I'm going to keep the force the same, 50 newtons. So let's examine what happens. So 50 newtons. And you can see that the increase in the speed is much less. We can also say that the acceleration is less. So by making the mass bigger, we've made the acceleration of the object smaller. So it seems to be that the acceleration of an object is inversely proportional to its mass. So that was 100 kilograms, and you can see how much the speed is increasing a lot slower. Let's reset things And rather using the 250 kilogram crates, let's go for the 200 kilogram fridge. So we shall keep the values the same up here, masses and speed. And this time we'll get the poor guy to move a 200 kilogram fridge. So that's twice as amount as well, compared to 250 kilogram crates. We'll use the same force, and there he goes. And you can see it's much harder to accelerate a bigger mass. And this is really the essence of Newton's second law. The bigger the value of the mass, the harder it is to accelerate for a given force. You can see the speedometer there slowly creeping up, which means that even this man's pushing with 50 newtons, the acceleration is a lot less. So we can learn a lot from that. We can learn that if we increase the mass for a given applied force, then the acceleration is less. It almost seems that the acceleration is inversely proportional to the mass. In other words, it's much harder to accelerate a big mass than it is a smaller mass. And now we begin to get to the real crunch of Newton's second law. So the results of our simulation gave us the following. When we have a constant mass and we apply a force to it, it will accelerate. If we in fact increase that applied force, we know that the acceleration is going to become bigger. So we can come to this conclusion. By keeping the mass of an object constant, the bigger the applied force results in the bigger acceleration of that object. So what we can write down now is a kind of maths term for this. We can write it in terms of the proportion statement. We can say that if we keep the mass constant, so it's a very important thing, we keep the mass constant, keep the mass the same, what we find out is that the acceleration is directly proportional to the applied force. We'll use small a for acceleration and capital F for the applied force. All that really means is if we double the force, we double the acceleration. If we triple the force, we triple the acceleration. So acceleration is directly proportional to the applied force, or in our case, the unbalanced force acting on the object. Our second piece of information was this. Keeping the force constant, the bigger the mass of the object produced the smaller acceleration of the object. Increasing the mass of the object and applying the same force resulted in a smaller acceleration. In other words, the bigger the mass of an object, the harder it is to accelerate that object for a given force. Now we can write that in this mathematical form. We can say that the acceleration is going to be inversely proportional to the mass. That means it's going to be 1 divided by the mass. We're using small m for the mass. What that means mathematically is that if you increase the mass of that object, the acceleration is going to decrease. And that's what we mean by inverse proportion. So now we've got two statements together. We know that the acceleration of an object is inversely proportional to its mass. And we know the acceleration of an object is directly proportional to the force which is applied to that object, the unbalanced force applied to it. And Isaac Newton put these two phrases together to produce the famous force equals mass times acceleration equation. We can write it like this. The acceleration is going to equal to the unbalanced force, or the applied force, the resultant force, divided by the mass of the object. And you can see from that equation, if we increase the force for a given mass, the acceleration is going to increase. And for a given force, if we increase the mass of the object, the acceleration is going to be smaller. Now we can rewrite that equation into the familiar Newton's second law of motion equation, which states the following. The unbalanced force acting on an object will produce an acceleration, and we can work out that acceleration from this famous equation here, F equals ma. Some people put down Fu, N, to stand for the unbalanced force. So if we've got an unbalanced force acting on something, it's going to produce an acceleration for that given mass. unbalanced force equals mass times acceleration.